internal combustion engines. When I am saying internal combustion engines, internal is inside, combustion it is a mechanism of heat generation, and engine is a device which is converting that heat into work. So, basically internal combustion engines are which is with the help of heat giving output. So, internal combustion engines are the machines which are responsible for taking some heat and converting that heat into work. It is just like human being. In the case of human being, some food we are giving, food we are taking, and that food inside the human body it is getting converted into heat. For conversion of heat, we need oxygen. Oxygen is responsible for the burning of the food which we have taken into the human body, and finally, we are getting energy into the human being. In the same fashion, in the case of internal combustion engine, we need fuel just like food in the human body. We need air for the purpose of combustion. It is not pure oxygen, it is a combination of oxygen plus nitrogen plus some of other gases. So, for the purpose of combustion we need fuel, it may be liquid fuel, it may be gaseous fuel. Liquid when I am saying it may be petrol, it may be diesel. Similarly, if I am saying gaseous fuel, it may be a natural gas, it may be LPG, it may be biogas, any type of fuel liquid or gaseous fuel may be, and finally, that fuel due to combustion it is getting converted into heat, and that heat is finally converted into work. So, it is the purpose of internal combustion engine that they are taking heat as a source of energy, and that source of energy, the chemical energy of that fuel is getting converted into heat, and finally, that heat is converted into work. Sometimes these engines are known as heat engines also. Meaning of heat engine is heat is the input and output is work. So, heat engines are in the category where heat which is a low grade energy, it is giving input to that engine, and finally, it is converting that heat into mechanical work, that is high grade energy. There is a difference between heat and work. Both are having same unit, it is in joules or it is in kilojoules, but their level is different. When I am saying low grade energy, it is heat. When I am saying high grade energy, it is work. Low grade energy is getting converted into work because it is low grade energy, and it is getting converted into work, that is high grade energy. So, the conversion of the total heat, because it is low grade energy, the total conversion is not equal to the heat which we have supplied to the engine. Always the work which we are receiving from the engine, it is lesser than the heat we have supplied. Suppose we have supplied 100 kilojoule heat to this heat engine, to this internal combustion engine, never will be receiving on the shaft 100 kilojoule work. It may be 40 kilojoule, it may be 30 kilojoule, it may be 25 kilojoule, but always it is lesser than the heat which we have given as an input. So, this ratio of the work output and heat input which we are giving, that ratio is very important, and this ratio is termed as thermal efficiency. Input is heat, output is work, output is high grade energy in the form of work, input heat which you have given, it is low grade energy. So, this ratio is very important, and our task is, our target is to increase this ratio. More efficient the engine, higher the work output from same heat input. So, when we are defining these heat engines, first of all, as per their definitions, always they are working in a cycle. All the heat engines are working in a cycle. When I am saying cycle, suppose I am at this particular point and I want to reach to railway station. So, from here to railway station, I will be following some path, I will be reaching there, and again I am coming to the same point, starting from here, reaching to railway station, coming back to this point, one cycle has been completed. In the same fashion, the processes which are taking place inside the engine while converging heat into work, there has to be a cycle. So, heat engine is operated in a cycle. Again I am saying purpose of these engines are basically converting the chemical energy of the fuel into useful work output. The diagram which I am showing you, fuel is an input, engine is a machine which is taking fuel as a source of energy, and finally, the output which you are receiving from this engine, it is in the form of mechanical power. All the vehicles which are moving on the roads, any vehicle, it may be car, it may be motorbike, it may be scooter, it may be truck, any vehicle which is moving on the roads, they are in the category of internal combustion engines. When we are designing these internal combustion engines, our first requirement is the efficiency of these engines should be maximum. Efficiency term when I will be using during the series of these lectures which I will be delivering under this head internal combustion engines, when efficiency I will be mentioning, I am mentioning for thermal efficiency. So, when we are designing these engines, our target is that thermal efficiency of an engine should be maximum possible. Meaning of this one is from given input, from given amount of fuel, the work output which we are receiving, that should be maximum. That is first and foremost requirement for an engine. Second one, the size of the engine should be small as possible. Work output should be more, but size of the engine, weight of the engine should be small as possible. So, the meaning of this one is the cost of the engine should be as small as possible. So, first target which we are having in our mind, that thermal efficiency of the engine should be highest possible, but with highest thermal efficiency, size of the engine should be minimum. The metal which we are using for the purpose of construction of these engines, that should be as less as possible, weight of the engine should be as small as possible, and the ratio of work output and the weight of the engine is termed as power to weight ratio. It is again very important term, just like thermal efficiency. Our target is power from a given size of engine, power output from a given size of engine should be maximum possible, but the weight of the engine should be small as possible. So, power to weight ratio should be as high as possible. Third requirement which we are having during this process of the fuel into this mechanical power, the exhaust emissions which are coming out, because when combustion is taking place, for the purpose of combustion we need fuel, fuel is having hydrocarbons. When hydrocarbons are reacting with atmospheric air which is carrying oxygen and nitrogen, during that combustion process many of the pollutants are being formed, just like CO, just like methane, just like oxides of nitrogen. So, many of the pollutants are formed. So, our target is that combustion process should be in such a way that exhaust emission should have only vapor, means H2O, vapor and carbon dioxide or nitrogen. So, the exhaust part should consist of CO2 plus H2O vapors plus nitrogen. We do not want carbon dioxide in exhaust, we do not want methane in the exhaust, we do not want any type of oxides of nitrogen. So, process of combustion should be completed in such a fashion that whole process is in the form of complete combustion, where exhaust emission is only CO2 and H2O. So, our requirement is the exhaust emission should be minimum. In today's world, the number of vehicles are continuously increasing. When vehicles are increasing, amount of exhaust emissions which are available in atmosphere, that percentage is becoming very high. Even breathing of a human being, breathing of plants, breathing of animals is becoming difficult. So, designers, the scientists who are working in this area, they are always concentrating to reduce the exhaust emissions. And fourth one is the running of an engine. The noise at the time of combustion which is created inside the cylinder, when combustion is going on inside the cylinder, pressures are becoming quite high, temperatures are becoming quite high, and they are resulting into very serious noise. So, our target is when we are operating these engines, their running should be very smooth. So, if I am concluding up to this point, heat engines are basically responsible for converting heat into work. When it is getting converted into work which is high grade energy, some of the heat remains unutilized, and that is why the amount of heat which we have given as an input, total heat is not getting converted into work. Our requirements are that this conversion should be maximum. This conversion is in the form of thermal efficiency, that is work output divided by heat input, that thermal efficiency of an engine should be maximum possible. Second one, the size of the engine which is responsible for converting this heat into work, that size should be as small as possible, and the ratio of work output divided by the mass of the engine, the weight of the engine, it is termed as power to weight ratio. This power to weight ratio always we would like to increase. Third, we want to have minimum possible pollutants into the atmosphere, and mainly the pollutants are hydrocarbons, carbon dioxide and oxides of nitrogen, and if it is diesel engine, it is particulate matter, it is smoke. So, our targets are that these emissions, it may be petrol engine, it may be diesel engine, these emissions should be minimum possible, and finally, we want running of the engine should be smooth, no noise, very less noise. If noises are less, if rate of pressure rise inside the cylinder is less, then maintenance of the engine will be quite small. These are the areas where one scientist, one engineer want to work. This diagram which is showing that we are having fuel for the purpose of generation of heat, we are having oxygen which is carried with nitrogen in air, and finally, when this air and fuel are reacting inside the cylinder, it is generating heat. That heat is finally getting converted into work, and heat is converted into work. These engines are also known as heat engines. The energy conversion process which is taking place, that is chemical energy of the fuel, combustion is taking place, and for the purpose of combustion we are supplying air. So, the chemical energy of the fuel is getting converted into heat with the help of air. That heat energy is inside the cylinder, it is in the form of very high pressure, it is in the form of very high temperature, which is forcing the piston to move in downward direction, and this movement is converted into a rotary motion with the help of a crankshaft. The movement of the piston is reciprocating, it is moving up and down, and finally, that movement is converted into rotary movement, that is mechanical energy. That mechanical energy is connected to a generator, the movement of the crankshaft is connected to the generator shaft, generator is rotating, generator is basically electrical device which is having a rotor, that rotor is rotating in a magnetic field, and final output is electrical energy. So, the processes which are taking place, the energy conservation process which is taking place, it is like this one fuel we are having, its combustion is going on, it is generating heat, that heat in an heat engine is giving work output, that work output is connected to the generator shaft which is rotating in a magnetic field, that magnetic field is resulting into an electrical energy. On this energy, on this electrical energy again which is high grade energy, whole life of human being depends upon. Our comfort, our the functioning of the all processes of the life of an human being depends upon electrical energy. So, the work which has been obtained from the engine with the help of heat, finally, it is getting converted into electrical energy. Sometime this process is termed as power plants, electrical power plants. These are electrical generators. In fact, the input we are giving with the help of engine, output we are giving electrical energy. So, prime mover is an engine and output it is electrical energy. Just example I am giving conversion of heat into work. Diesel engine example I am giving, diesel engine where fuel is diesel. It has been invented by scientists diesel. somewhere in 1896 this diesel engine has been developed, where heat addition process or combustion of fuel is very special. When heat is being added into the combustion chamber, more or less pressure remains constant hypothetically. So, heat addition process in the case of diesel engine is at constant pressure. After combustion of fuel inside the cylinder, pressures inside the cylinder becomes quite high, it is forcing the piston to move in downward direction. The energy of the fuel which is carried by the combustion products, it is forcing the piston in downward direction. After releasing its energy to piston, those burnt products are going out in the form of exhaust, it is being shown. So, finally, work output is at generator in the form of electrical power output, and thermal efficiency I am defining here. It is shown as shaft power output divided by power available in the fuel. Shaft power output is work output and power available in the fuel is calorific value of the fuel multiplied by the mass of the fuel which has been utilized for the purpose of generation of this power output, and our target is this thermal efficiency should be as high as possible. Normally, the value of this thermal efficiency, if I am saying petrol engine, it is around 25-26%. In the case of diesel, it may be up to 30%. Meaning of this one is the input which we have given of that one, in the case of diesel only 30% is getting converted into useful output. If it is petrol engine, the spark ignition engine, then conversion efficiency is 25-26%, remaining heat is going as waste. So, again target is that the wastage of heat which is being done, can it be reduced, can we obtain 100% efficiency, that is the dream of the scientist. Target is that amount of heat which has been supplied, can it be converted 100% into useful work. This thermal efficiency value we want 100%, that is the dream. However, practically it is not possible. When the series of the lectures will be going on, I will be explaining what are the reason why this conversion of heat into work 100% is not possible, how this conversion is low. Just one example I am showing you heat addition. Heat addition inside the combustion chamber. Normally, the working fluid which we are having, it is air. The ideal Otto cycle or diesel cycle, Otto cycle we are using for spark ignition engines, the diesel cycle we are using for diesel engines. In this cycle, the heat addition process, hypothetically the source of heat which we are having, Q which we are having, it is outside the cylinder in these cycles, Otto cycle, diesel cycle, and they are termed as air standard cycles also, because heat is due to combustion, it is outside, the hot body is outside the cylinder, inside the cylinder only air is there. You can see Q is heat input from outside the cylinder, the volume V1 which is being shown, it is volume of air. So, when heat is being added to this air, the temperature of air due to addition of heat can rise, but same time in some of the processes we want that when heat is being added, temperature of air should remain constant. It can't remain constant. If heat is being added, internal energy of the air will be increasing. So, temperature should increase, but same time the another part of the engine which is shown in the form of piston, if same time piston is moving which is responsible for the expansion of air, it is resulting the temperature of it is decreasing the temperature of air. So, one side we are adding the heat, it is trying to increase the temperature of air, but same time due to the movement of the piston, expansion is taking place, temperature will be decreasing, net effect may be a constant temperature heat addition, and this process I am showing from 1 to 2. The x axis is showing pressure, y axis is showing volume. In this PV diagram, the movement of the piston is from 1 to 2, where volume of air which is inside the cylinder, volume of air is increasing from V1 to V2. From V1 to V2, when volume is changing, temperature remains constant. 1 to 2, the expansion process which is being shown, it is just an isotherm. Isotherm means temperature remains constant. Temperature between T2 and T1 is constant. If this type of heat addition process is there, the probability of conversion of heat into work becomes maximum. This type of process is a reversible process, and when this process happens inside the cylinder during heat addition, the 100% conversion of heat into work is possible. We want to achieve this type of process, particularly when heat addition is taking place. So, again it is a dream, it is hypothetical. In actual engines, this type of heat addition is not possible at all. In Carnot cycle, we will be studying this Carnot cycle also during this process. In hypothetical Carnot cycle, where working medium is air, source of heat is in the form of an hot body which is outside the cylinder. The cylinder is a very good conductor, it is transmitting heat from the hot body to air and responsible for expansion of air, and in this process conversion of heat into work is maximum, but in actual engines this type of process is not possible at all. Finally, if you see W equal to Q, it has been shown, means whatever heat has been given during this process, that has been converted into work. Area under this line between V1 and V2, the area which has been shown, it is equal to work output. So, the amount of heat which has been transmitted, amount of heat which has been supplied, that has been converted into work. So, this is an example of Carnot cycle which is meant for hypothetical heat engines. Even in these engines also, even heat addition is through the process which is being followed, it is reversible process, but still remaining processes for completing the cycle somewhere will have to reject the heat. I will be explaining that one. Due to that one, the efficiency of Carnot cycle is even not 100%. You see the example of internal combustion engine. Internal combustion engine, we are saying the combustion which is taking place, it is inside the cylinder, the flames are visible to you. Here, if it is petrol engine, inside this cylinder, in one process of suction, we have supplied air plus fuel vapors into the cylinder. If it is petrol, air plus petrol vapors are available inside the cylinder during suction. If it is natural gas engine, then air plus natural gas mixture is available inside the cylinder during suction, and that air plus fuel mixture we are compressing. Just after compression, some source of ignition, some intense source of ignition is being provided. That intense source of ignition is resulting into combustion. It is in the form of flame, it is visible. That flame is propagating inside the cylinder, it is capturing air and fuel mixture which is available in every corner of the cylinder, and temperature and pressure inside the cylinder becomes quite high. That high temperature and pressure is forcing this piston into downward direction. This combustion process is taking place in a cylinder where piston is available, some more components which are responsible for supplying the air fuel mixture, for exhausting the burnt products. So, many components are there, but combustion is taking place inside the cylinder. That is why these engines are termed as internal combustion engine. The space where combustion is taking place, it is clearance volume, very small volume where the air plus fuel mixture has been compressed. If it is spark ignition engine, if it is petrol engine, normally the compression as compared to total volume, it is roughly 1/8, means after compression the volume which is there inside the cylinder where flame is visible, it is roughly 1/8 of the total volume of the cylinder. If it is diesel engine, then this ratio is roughly 1/15, means it is compression. After compression, inside the cylinder pressure and temperature of that air fuel mixture in petrol engine is significantly higher, and in that atmosphere when spark is initiated, combustion has been started here, and that is forcing the piston into downward direction. Piston is moving downward. When stroke will be completed, that is power stroke will be completed, movement of the piston in downward direction is completed, again piston will be coming in upward direction. So, like this one, continuously piston movement is possible inside the cylinder, means piston is reciprocating from upper part to lower part, from lower side to upper side, it is reciprocating, and the reciprocating movement of this piston is getting converted into rotary movement of the crankshaft, and that is finally responsible for giving the work output. Even heat addition process may be like this one also. Again there is a cylinder piston mechanism, the colored view which is visible, again it is air, heat source is outside, Q in which I am saying. So, Q in is given in such a way that pressure inside the cylinder 2 to 3, again pressure volume diagram, TDC to BDC positions are shown. TDC stands for top dead center, BDC is bottom dead center. Between these two limits piston reciprocates. So, when it is moving from TDC to BDC, part of the movement, the process is in such a fashion that pressure inside the cylinder is constant. When we are adding heat, pressure has to increase, but same time because piston is moving, volume inside the cylinder is increasing of the air, the process of heat addition is constant pressure, but this is not reversible process. The Q in which we are giving, it is not reversible process. If you remember in earlier slides when I was explaining the heat addition process, isotherm when I was explaining, in that case I was saying when heat is being added, temperature inside the cylinder is constant. Here the process is different. Here when heat is being added, pressure remains constant. When pressure remains constant, this type of heat addition process is not reversible. Meaning of this one is the amount of heat which has been added, 100% it has not been converted into work, because some of the heat has been lost in irreversible happenings which are there inside the cylinder. The diesel engines or the diesel cycle which has been devised by diesel, that is working on this cycle hypothetically. Here we are assuming that working fluid is air, heat is being added with the help of some external source, piston is moving towards the bottom dead center, part of heat addition which is there, that is at constant pressure, and remaining again from 3 to 4 if I am saying, it is reversible heat addition, reversible expansion, mean part of this stroke is at constant pressure, part of this process heat addition at when process is following reversibly, the movement of the piston, the expansion is taking place with reversible process, and sometimes it is being said reversible adiabatic process. When I am saying reversible adiabatic process, no heat transferred from outside to the cylinder or cylinder to outside in the surrounding, no heat is being transferred, and reversible means even the movement of the piston is not facing any type of friction also. So, hypothetical again assumption that there is no friction and there is no heat exchange between 3 to 4, but 4 to 1 process is a heat rejection process into the surrounding. So, heat which you applied Q, part of that is getting converted into work, but some of the heat has to be rejected into the surrounding. If some heat has been rejected into the surrounding, that heat has not been utilized for the purpose of conversion of that heat into work. That is why efficiency of this type of cycle is not 100%. Even in Carnot cycle, some of the heat has to be rejected for the completion of the cycle. In the same fashion, in diesel cycle also, this 4 to 1 process is responsible for decreasing the efficiency. Even 2 to 3 process is also responsible for decreasing the efficiency. 1 to 2 again for the purpose of completion of the cycle, piston moves from BDC to TDC, this is compression process, again it is assumed to be reversible process. So, from 3 to 4 and 1 to 2 there is no loss of heat, but from 2 to 3 and 4 to 1 the conversion is from Q to W conversion is irreversible process. That is why these type of cycles are having efficiency less than even Carnot cycle. I am saying Carnot cycle is not 100% efficient, but this type of cycle is for having efficiency further lower, and it is just like joke when we are saying diesel cycle somewhere in I said in 1896 this cycle has been devised, it has been devised by diesel. So, someone is saying then who has devised the diesel fuel? Diesel has devised the diesel cycle, who has devised the diesel fuel, from where this diesel name came for the fuel also. Name came, maybe different names before 1896, but because this type of fuel, special type of fuel is being used in the constant heat addition process in diesel cycle, the name of the fuel has also been converted in the name of diesel. Another type of heat addition process, normally it is in spark ignition process. I am explaining here how heat is being added inside the cylinder for converting into useful work output. So, heat addition one process I have shown where temperature during heat addition remains constant in Carnot cycle. Another cycle I have explained where heat addition is a constant pressure, that is diesel cycle. Another type of cycle I am explaining where heat addition is at constant volume. Again your vertical axis is having, y axis is having pressure, x axis is having volume. 1 to 2 if we observe your volume is constant and that time heat being added. Constant volume heat addition means without consuming any time, if total heat suppose 100 kilojoule heat has to be supplied to the air without consuming any time, instantaneously we have added the heat from 1 to 2. There is rapid pressure rise from 1 to 2. Again this process is not reversible process. Addition of heat between 1 and 2 at constant volume, it is irreversible process, and after that 2 to 3 the expansion process is taking place. Expansion process in this cycle is assumed as reversible process. This type of cycle where heat addition is at constant volume, it is Otto cycle, and all spark ignition engines are working on this principle. So, 1 to 2 is heat addition, 2 to 3 is expansion, reversible adiabatic expansion, again 3 to 4 is heat rejection to the surrounding. When heat rejection to the surrounding is taking place, again there is loss of some heat to surrounding. So, again the efficiency of these type of engines won't be 100%. The compression process from 4 to 1, it is reversible adiabatic process. To 2 to 3 and 4 to 1, it is reversible, there is no loss, but between 1 to 2 where heat is being added, it is not reversibly added, and 3 to 4 where heat is transferred to the surrounding, this is also irreversible process. So, this type of cycle is also not 100%, but if at the same pressure values, if same starting pressure values, if it is getting converted, this cycle is better than the diesel cycle which we are referring. Means heat addition is constant volume is much more advantageous as compared to constant pressure heat addition as far as efficiency is concerned. Another parameters, another effects on the engine which are coming due to this type of heat addition we will be discussing later on, but till this point again if I am concluding heat addition process, three type of heat addition process we have discussed, one at constant temperature, another one at constant pressure, third one at constant volume. Out of these three if I am comparing, the best one is heat addition is at constant temperature. At second number if I am saying heat addition at constant volume, third is heat addition at constant pressure from efficiency point of view, thermal efficiency point of view. So, one heat addition when it is at constant temperature, it is Carnot cycle. When heat addition is at constant pressure, it is diesel cycle. When heat is being added at constant volume, then it is Otto cycle. The comparison of heat which has been supplied and the amount of work which we have obtained on the output shaft, the comparison is shown here. In the engine, the example has been given that 100 units of energy per hour being supplied to this engine. Out of that 21 units of heat has been transferred to cooling water. Every engine has to be cooled, because the materials which we are using for the purpose of framing the cylinder or constructing the piston, they are having certain limitations as far as sustaining the temperature is concerned. Above certain limit they can't sustain temperature. Normally the piston and cylinder which we are having, they are having cast iron as metal or mild steel they are having, or aluminum they are having, which are having certain limitations as far as their melting points are concerned. 1500 degree Celsius temperature if it is reaching inside the cylinder, your cast iron or mild steel can melt. Cast iron can melt even at 1150 degree Celsius, aluminum can melt more than 700 degree Celsius. So, if temperature is becoming above certain limit, chances of melting of these cylinders are. So, for sustaining that much heat, for sustaining that much high temperature, continuous cooling of these engines has to be, it may be air cooling, it may be water cooling. but when we are doing cooling, some of the heat is also getting rejected and finally, it is going into the atmosphere, where there is no use of this heat, means it is wastage of the heat. So, 100 units of the heat which is applied, intensely 21 units of heat were rejected into the cooling medium, which is water or air it may be. Between cylinder and piston, because piston is moving inside the cylinder, both are metallic. If metallic components are there, it will be having lot of friction also. So, some of the energy, the heat energy which is applied, it is being wasted into overcoming that friction. For reducing friction, some of the oil it has to be, lubricating oil it has to be between the wall of the piston and wall of this the cylinder. There has to be some mechanism, so that friction can be reduced. That reduction is with the help of oil. So, this oil is also storing some of the heat. For heating that oil, some of the heat is needed. So, out of that 105 units of heat has been given to that lubricating oil also. So, 21 with cooling water it has gone, 5 it has gone with lubricating oil. Then, because temperature of the cylinder is significantly higher as compared to atmospheric conditions. So, some of the heat is rejected due to radiation, some of the heat is rejected to direct convection also. So, heat radiated to surrounding is 1 unit per hour, that is again wastage of the heat. And the burnt products, finally after combustion during exhaust stroke, the burnt products which are going out, it is having also temperature higher than atmospheric. When we have sucked the air into the cylinder, its temperature was atmospheric, but after combustion, the burnt products which are going out into the atmosphere, they are having their temperature higher than atmospheric. It means some of the energy they are carrying with us, that heat they are carrying with us, and it is significant amount which is going out with the burnt products. So, here in this example, 32 units per hour heat has been rejected with these burnt products. So, useful heat which is available on this shaft of the engine, it is only 41 units. Out of 100 units which we have supplied, 41 units we are getting on the output shaft. This 41 divided by 100 is becoming our thermal efficiency. So, value of thermal efficiency is 41 divided by 100 multiplied by 100, when we are converting in terms of percentage. So, it is coming 41%. Meaning of this one is only 41% heat has been utilized for the purpose of conversion into heat. Very old system I am showing you, where tires were also not of this nature, where we are having now rubber tires we are having. They were using some solid tires, wooden tires they were using in olden days. Even body of the vehicle was wooden, even steering mechanism, the mud guards, everything was of those metals which were available that time, mostly leather and wood was available. So, those type of mechanism in olden vehicles were there. Today, if I am comparing the bodies of plastic, engine parts with aluminum, many different metals, composite metals, low cost metals, special metals which can sustain very high temperature. When aesthetic point of view, if I am comparing life of the metal, if you are comparing strength of the metals, we are comparing, various type of metals are available. So, everything has changed as compared to the theme of the auto, as compared to the theme of the diesel. Many of the things have been changed. You see the earlier applications of the engine, if you see, earlier men they have utilized these engines either for taking water from underground for the purpose of drinking, for the purpose of irrigation. They have started the application of these engines. Then in some of the areas where this fodder cutting machine is needed, so those were the applications. In the case of lifting of the water, in the case of moving some of the heavy components, those were the applications. Now, majority of the vehicles which we are using, it is for the purpose of transportation, even this electrical generation, even the processes which are helpful for the human beings. So, many applications of these engines are as compared to earlier days, and this see the many of the vehicles which are moving on the road, all varieties starting from two wheelers to many wheels vehicles are having. These are the buses, cars, even difficult to monitor them. Various type of vehicles we are using which are being operated by these internal combustion engines. So, different application of these internal combustion engines are shown on the various type of vehicle which are visible on the road. One video I will be showing you that how this internal combustion engine is functioning, what are the parts of this internal combustion engine and how it is working. I think you will be understanding in a better way after going through this video the functioning of this internal combustion engine. Here you see different parts are indicated here of this whole complete engine. Inside the engine, one component which is reciprocating, it is termed as piston. Inside a space where it is rotating, it is cylinder. So, in the cylinder, piston is reciprocating. For taking fresh air fuel mixture into the cylinder, valves are available. For exhausting the burnt products from the cylinder, the exhaust valve is available, which is hottest component of the engine. For starting the combustion of the fuel, there is a spark plug. For operating these valves, we need one camshaft which is having cams there. Those cams are responsible for opening and closing of these valves. Rocker arms are moving up and down as shown into the figure. They are pushing the valves in downward direction against the spring force. The valves are being opened. Due to opening of the valve, fresh mixture is entering into the cylinder. After filling up the cylinder with fresh mixture, the valve will remain in closed position and piston will move in upward direction, which is compressing that mixture. And after compression, there is a spark plug. Spark plug is also visible in this diagram. That spark plug is initiating the combustion into the cylinder. It is forcing the piston in downward direction due to generation of heat, due to creation of very high pressure into the cylinder. So, the piston is moving in downward direction. The piston is connected to crankshaft with the help of a connecting rod, which is continuously rotating. The crankshaft is rotating. The crankshaft is housed in a crankcase where lot of lubricating oil is also being provided for reducing the friction of different components of the engine. So, major components of the engine are rocker arms which are operating the valves. We are having camshaft which is rotating, which is giving work input to the rocker arm for the purpose of opening of these valves. Valves are responsible for bringing down bringing into the fresh mixture in the cylinder and exhausting the burnt products. Piston is reciprocating, which is converting the chemical energy or heat energy into work. Crankshaft is rotating, giving useful output. Crankcase is housing the crankshaft. It is carrying the lubricating oil also into this one. Connecting rod is a component which is connecting piston and crankshaft. Cylinder is housing the piston into this one, and some jackets are also shown which is carrying the cooling water, which is maintaining a constant temperature inside the cylinder, because lubricating oil has to be on the cylinder walls. If temperature becomes quite high, the temperature of lubricating oil become quite high and it won't be it won't remain on the cylinder walls. Normally, the temperature of cylinder wall is around 300 degrees Celsius, where the viscosity of the lubricating oil is sufficient and it won't flow much, otherwise it won't stick on the cylinder walls. The movement is visible, the different processes are visible. Yes, green is fresh mixture is coming into this one. When combustion is going on, it is gray. So, this is functioning of the engine. This is functioning of the engine. Rotary movement, reciprocating movement of the piston is getting converted into rotary movement of the crankshaft. I think functioning of this internal combustion engine is clear from this one. This view you see, this is cylinder and piston. Cylinder is outer one, inside that one even a piston is visible. They are having very smooth surfaces, so that friction should be minimum. When piston is reciprocating inside the cylinder, friction should be minimum. The holes which are visible, these holes are basically water jackets. It is carrying the cooling water into this one. The metallic components which are there, it is either cast iron, in some cases it may be aluminum also. Both cylinder piston can be with aluminum metal. The objective is the weight of this cylinder piston should be small as possible, strength should be quite high, even a higher temperature they should maintain their shape and strength. So, this is a combination of piston and cylinder which is being utilized for the purpose of combustion. the combustion is taking place inside this space which is visible. It is the one another view is also shown how with piston the connecting rod is connected, one pin is visible, that pin is known as guzzen pin. One end of the connecting rod with the help of this guzzen pin is connected with the piston, it is known as smaller end of this connecting rod. Another end of this one is bigger end, that bigger end is connected with crankshaft. So, the reciprocating motion of this piston with the help of this connecting rod, the power is going on the crankshaft and that crankshaft is rotating. Another type of mechanism I am showing you, it is in gas turbines. It is also an example of internal combustion engine where air is taken from atmosphere in the compressor. The inlet is shown at number 1, in compressor it is coming, compressor is compressing that air. At number 2 it is entering into a combustion chamber where continuously fuel is injected, the combustion is going on, high temperature gases are being formed there. The high temperature gases are passing over the turbine is rotating, and finally it is connected to power turbine which is responsible for operating the gas turbines. It may be in terms of electrical energy also from that turbine. Finally, we are getting soft power output in the form of electrical energy. Here the power which we are getting directly, it is rotary movement, it is not reciprocating movement of the piston. So, in the case of turbines, the work output which we are taking directly from the turbine we are taking, and which is continuously rotating. If combustion is not taking place inside the cylinder, somewhere else if it is taking place, the type of heat engines are termed as external combustion engine. One example of that one is steam engine. You can see clearly here, there is a combustion chamber where coal burning is taking place. It is a solid fuel where combustion is going on. Those hot gases, they are transferring their heat to water. So, in the case of internal combustion engine, there was one working fluid which was having air, which was working, which was having fuel, which was having some residual gases, and it is a mixture of all these three. But in the case of external combustion engine, again we are having the burnt products, we are having air, we are having some other residues also into this one, into the mixture, that is one working fluid, and that working fluid is giving heat to water. That water is getting converted into steam, high temperature, high pressure steam. That high temperature, high pressure steam is forcing that piston and it is moving the piston, again reciprocating movement, and that reciprocating movement with the help of connecting rod, it is directly going on the wheels are rotating and it is making that steam engine to move. The exhaust products which are taking place due to combustion is going through chimney into the atmosphere. So, the difference between these two type of engines are, here combustion is taking place outside the cylinder, another one there are two working fluids, one is the burnt products or air, another one is steam which is responsible for giving useful work output. And this engine also I will be showing you how this engine is working, how this engine is giving useful output when combustion is taking place outside the cylinder and working fluid is in the form of air plus burnt products and in the form of steam engine.
Steam engine propelled the world into a new age of transportation. Popular legend has it that 18th century inventor James Watt discovered the power of steam when he observed the lifting lid of a kettle of boiling water. The truth is that man had been aware of the power of steam for countless centuries, long before Watt ever sat down for his first cup of tea. As early as 100 AD, ancient writings told of a rotating steam turbine wheel created by Hero of Alexandria. The device was described simply as a sphere of Aeolus, but Hero never realized the potential uses of his creation and dismissed it as nothing more than a simple toy to keep a drowsy emperor awake. It would be nearly 2,000 years before a practical steam engine would be invented.
The steam engine was originally conceived to pump water out of very deep mines, and it soon became applied to lots of other things, especially for driving all sorts of mills.
Most closely associated with the creation of the steam engine is 18th century English engineer and inventor Thomas Newcomen. Newcomen designed and built one of the first practical atmospheric steam engines around 1712. The steam engine consisted of a series of steam-driven piston rods linked by chains that rose and fell in order to lift water out of mines. For over 50 years, Newcomen's steam engine set the standard, but a Scottish instrument maker and engineer, James Watt, set out to improve on Newcomen's creation.
Initially, the rotated motion wasn't used with atmospheric engines because they weren't very evenly running engines. James Watt, by applying steam to both sides of a piston in a cylinder, and with the use of properly designed valves, could impart a regular rocking motion to a beam, and by means of a crank, then rotate a wheel.
This improved steam engine, aided by the wheel, provided a major advance in the way we traveled over water. By the late 1700s, the steamship was man's first major development in traveling great distances since the creation of the sail thousands of years before. The French were the steamship's earliest pioneers in the late 1700s, but it was an American, Robert Fulton, who first achieved commercial success when he gained worldwide attention for driving his steamship the Clermont between New York and Albany in 1807.
So, both type of engines we have seen, internal combustion engines and external combustion engines. Similarity between these two are both are converting heat into work. Dissimilarities are internal combustion engines are having combustion inside the cylinder, external combustion engines are having combustion outside the cylinder where steam is getting generated. And in the case of internal combustion engine, only one working fluid we have observed, whereas in the case of external combustion engine there are two working fluid, means the burnt products and the steam, two working fluids are there. Some of the examples of external combustion engines are shown, the railroad it is there, even the thermal power plants which are working, they may be using coal, they may be using natural gas. With the help of that heat, water is getting converted into steam, that steam is being utilized for the purpose of operation of the turbine, and that the final output of the turbine is electrical energy. It is clearly indicated that one. The aircraft which I am showing you, it is having gas turbine as a prime mover, which is internal combustion engine. So, both internal combustion engine and external combustion engine examples are shown here. Working fluid are compared, that in the case of internal combustion engine, air plus fuel plus residual gas is a working fluid, whereas in the case of external combustion engines, the working fluids are two working fluids, that is burnt gases and another one is steam. So, those are the working fluids. On the basis of this one, it can be compared. Then I am saying fuel combustion, if you are observing, both are internal combustion examples, where inside the cylinder combustion is taking place. So, fuel is being burnt into the cylinder, whereas in the external combustion engine you see, when combustion is taking place, it is outside the tubes which are responsible for generating the steam. So, in external combustion engine, combustion is taking place outside the engine, that example is also clearly indicated here. It is a boiler, and inside the boiler heat is getting generated, that heat is converting water into steam. That steam may be superheated, that steam may be wet steam, that may be saturated water according to requirements. If sizes, if you are comparing, for the same power output, size of the internal combustion engine is smaller as compared to external combustion engine, and even in terms of power to weight ratio, because that is another measurement of the engine performance. Power to weight ratio, if I am comparing, internal combustion engines are having better power to weight ratio, higher power to weight ratio as compared to external engine. Means for the same output, if I am comparing, size of the external combustion engine is large as compared to internal combustion engines. These heat losses are indicated here. 100% heat which is being supplied to the engine cylinder, majority of that heat, more than 62% has been gone as loss in the form of cooling water, in the form of burnt products, in the form of irreversible processes which are taking place, or many accessories we are operating, the lot of friction is being there, and when finally through transmission system it is going on the rear wheels, only 12% of the total energy which we have given to the engine, 12% is getting transmitted. That 12% energy is being utilized for the purpose of movement of the vehicle in forward direction. It is overcoming the resistances which vehicle is facing. Normally the resistances are the rolling resistance on the road when vehicle is moving, that rolling resistance is there. According to the speed of the vehicle, air will be forcing in reverse direction of the movement of the vehicle, that is air resistance also it will be having, and if vehicle is climbing higher gradient, then gradient losses are there. So, whatever output is being received by the wheels, that is basically to overcome the resistances in the form of rolling, in the form of air resistance, in the form of gradient resistance. These are again heat losses in the form of heat balance sheet. I am showing you that roughly 33% heat is going in exhaust gases, 24% it is going in cooling water, then 38% it is going from the engine, but some of the accessories friction losses are also there. So, really on the engine output shaft, crankshaft, it is coming 33%. So, majority of the heat which we are supplying, it is going as waste. So, our target is to reduce these losses, maybe exhaust losses, maybe cooling losses, maybe frictional losses. Our target is to reduce them, and same time when it is being added, irreversibilities which are available, it has to be reduced. Advantages of ICE engine over external combustion engine. Most of the engines which we are using these days, those are internal combustion engine, particularly when they are not stationary. For stationary purposes, we can use these external combustion engines, but for mobile applications we are having internal combustion engine. They are relatively cheap, their power to weight ratio is quite high, their efficiency means thermal efficiency, if I am saying, significantly higher as compared to external combustion engine. However, in some of the exceptional engines of external combustion engine, where efficiency of external combustion engines are higher than the internal combustion engines, and even exhaust emissions in the case of internal combustion engines are being controlled up to a certain limit by controlling the spark timing, by controlling the compression ratio, by design changing the design parameters. Even treatment of the exhaust is being done, so that exhaust emissions as compared to external combustion engines are controlled in a closed limits. Some of the question which can be very important related to this lecture, one is what is the difference between these two. I explained in detail that what is the major difference between external combustion engine and internal combustion engine. The major difference which is visible here, that is the combustion processes which are taking place in internal combustion engine, it is inside the cylinder, external combustion it is outside cylinder, and normally the speed of the crankshafts in the case of internal combustion engines are significantly higher as compared to external combustion engines. That external combustion engine are explained here also. In the case of internal combustion engine, the heat which is being added, it is timed heat addition, at one particular time it is being added, whereas in external combustion engine continuously heat is being added. The working fluid which is there, it is continuously being heated. If it is not required, if electrical output is not required or movement of the heat engine is not required, that time even heat addition can be controlled also. Then fuel economy point of view, we have compared, in most of the cases efficiency of internal combustion engine is higher, but as I said, in special cases, in some of the special cases, even this thermal efficiency of external combustion engine can reach between 40 to 50%. So, significantly higher efficiency we can obtain in recent external combustion engines also. I hope you have enjoyed this lecture. Thank you very much. Next time we will be discussing different type of efficiencies of the engine on which performance of engine depends.